Okay, so I didn't finish my presentation, but at least we have something to start with. So we talked about different, I'll check the sound, different generation approaches like GANs, variational autoencoder diffusion models. And today we will talk about another approach, which is called optimal transport. Mm, it's pretty recent topic, uh, and I think it will be as well as popular as diffusion models, maybe in a few years. So there are different formulations. Well, actually, this is old topic. It appeared in during World War II, and the well, actually, it appeared during Napoleon War first, but like recent formulation during World War II. So we'll talk about discrete optimal transport, continuous and neural optimal transport. So you all have heard about this transportation problem when we have some um, warehouses and warehouses, sorry, and markets, and uh, the stores want to buy to purchase the goods from different manufacturers, and of course they want to minimize the cost for the transportation of these goods. And here's this illustration that we have possible uh, transportation, what's called ways, roads, or options, and every uh, path has its own cost. You can think about this like in the simplest setup as distance and cost for the gas to transport the goods along this road. And we want to minimize the cost. And also you can think about like one store may have a demand of more products than one of these manufacturers has. So we will need to all order these products from several maybe um, places. And we want to minimize the cost of the transportation. So this is the transportation problem, how it's known from 50s and 60s, and it's solved with, it can be solved with algorithm which is called flow um, network, the maximal flow in the graph. Um, so the first formulation of this problem was made by Gaspar Monge, was a mayor of some French city during Napoleon, and also he um, went to an expedition. Well, they called this expedition, but of course it was a war in Africa, and um, so also he also fight with Napoleon, and he was thinking about the problem, how to um, dig the trenches. So how to move some earth, some dirt from one place to another place. And if you think about like more modern formulation, we have an area, for example, in three-dimensional space U and another shape in three-dimensional space V. And we want to move the transform one shape into another shape. Um, and if we think about the work, and in physics, the work is formulated as the integral over the distance. So we want to minimize this work, this integral over L1 distance between current data, current dot, for example, and the new position. And new position is given by some transformation function t. In practice, currently we mostly work with square distance instead of L1 distance. And the formulation, so if you normalize these objects on the manufacturers, suppliers, so we have like integer numbers of products. If you normalize these numbers, you will get probability, you will get distribution. So the same problem can be formulated in probabilistic setup. So we have two distributions, x and y, with some sigma algebras and some probability measures on these distributions. And we want to find a function. It's called measurable function, Borel function, which means that for maybe it's so much details. It means that for any subset of our which is called sigma algebra Q, the inverse, the preimage of this subset will belong to the sigma algebra of Q. So this is just the definition of Borel function. And we want to find, but you can think about this just about like some function which will minimize a cost. So now this C stands for a cost which can be L1 distance, L2 distance, cosine similarity, some cost function between our original data and our transformed data. And yeah, we want to find this transformation that results in the smallest value of this cost. So, like in this example, we have distribution P, distribution Q, and we have some paths. For example, if you think about cost as distance, then you can understand that it's more expensive to connect xy with this point t of x2 because we will have longer distance. So optimal transport, actually, if we use Euclidean metric, will result in this non-intersecting paths. And later we will talk about connection with diffusion models, because diffusion models will perform this transportation, but with a noisy trajectories. And the optimal transport will move your data just in one step instead of multi-steps like in diffusion models. The problem with this approach, with Monge approach, is that it doesn't work for discrete data. So, for example, if you have distribution P, a distribution P just one point, and if you have a distribution Q 2 points, or you can think about Q as continuous distribution, for example, normal distribution, you can split 1 point into continuous distribution or 2 points. And that's why instead, so you can find a transform T that will map 1 point into 2 points because T of X will be just 1 point. So that's why we will use another formulation from, as I said, 1940s, which is called Kantarovich relaxation of this problem. So Kantarovich was working on a problem how to use in most efficient way fanier for airplanes during the war. So how to use this fanier in more efficient way, how to solve these faniers so you have less what's called trash from the rests. So here formulated this problem as follows. Instead of looking for a transformed T, we will actually try to find a conditional, oh, sorry, a joint distribution. So I hope you know, you understand what does it mean joint distribution. Like if you have the two-dimensional Gaussian, for example, you can take a projection on one dimension, on one x, and if I draw this in three-dimensional case, so Gaussian will look like this. So it's three-dimensional plot. And if you take a section or projection or marginal distribution, as in the section, you will have just one-dimensional Gaussian. So Kantarovich proposed to kind of to work on this product of spaces to find the joint distribution phi such that the projection on for example x will coincide with distribution on our sources, with distribution p, and projection on this space y should coincide with original distribution of demand in our domain y. So if I draw this example with 1 and 2 dots, now you can understand that it will work, because if this is our x, for example, and this is our y, now we can find, so joint distribution p o, well, they use pi of x, y, can be given by these two dots, and then projection on x will result in 1 point, and projection on y will result in 2 points. So, but there there are many ways to, for example, for continuous distribution, if you think about like uniform distribution on one uh, um, on y and on x, then there are actually infinitely many joint distributions. So, for example, if I draw just straight line, its projection on y will result in uniform distribution. Its projection on x also will result in uniform distribution. If I draw, for example, this curve, its projection also will result in uniform distribution on both. Well, I'm not 100% sure, but I just want, my point is that there are many multidimensional shapes that have the a given section, but they will be different. A given section uh, for, for example, y equals 0, but they have different sections for different values of y. Okay, so and now the problem is formulated as follows. Instead of looking for function t, we will look for the uh, joint distribution pi. The joint distribution pi such that projection on x coincides with our um, manufacturer's plan, and projection on y will coincide with demand. So, and this function is called transportation plan. And again, we will minimize the cost between x and y. But now we don't use t of x, we just use y. Kind of work with two variables. Yeah, and here is example that now actually we can move parts of our goods from x1 to y1, parts to xy2, and parts to ym. So, and we're not limited to have the same number of points here, so we can have different number of points. And this is the classical transportation problem, which people typically learn in class, in optimization class, like when they learn linear optimization problems. This problem also can be formulated as linear optimization problem. And the question is how to learn this joint distribution pi. Uh, okay, maybe before we go into the joint distribution, I will show you the result, how we can apply this discrete optimal transport to the task of voice conversion. So I hope you understand now general idea that we have the distribution of one data, distribution of another data, and we want to kind of move one distribution to another in to minimize some costs. So in case of voice conversion, so we have a Libre speech data set, and you remember this data set has recordings of different speakers, and also I will use with LM model, which is similar to Hubert. As you remember, last time we talked about Hubert model that um, creates embeddings for audio, for raw audio. Um, and I didn't mention about Whisper, but maybe I'll talk about Whisper later. So WebLM also creates embeddings for audio for every 20 milliseconds of audio. It creates the vector representation. And also there is another model, Hi-Fi Gun, which reconstructs, which transforms back the vector representation of audio into waveform, um, which is called vocoder. We will talk about vocoders next week when we will talk about audio synthesis, speech synthesis and audio synthesis. As you remember, the layer where embeddings more similar to spectrograms is 7 or 6 layers. So we'll take as embeddings the 6th layer of this model. And after that, here is our cost function. Cost function. In this example, we will use cosine similarity, but 1 minus cosine similarity, because most similar vectors should actually have the smallest cost for transformation. Um, and there is built-in Python optimal transport library that performs this classical optimal transport in Kantarovich formulation. It's called discrete optimal transport, which maps one vectors into another vectors. Um, the the plan, the distribution of the source and target, we will just use the uniform distribution, just 1 over number of data points. So this will be our P and Q distributions, uniform distributions. Um, okay, where is okay? So we read the audio recordings for specific speaker that's given speaker identity, and so here is the result. For example, for speaker with ID 103, we have 102 recordings, and for speaker with identity 1034, we have 96 recordings. And then I apply optimal transport. So here I create the list of embeddings. So get features will return vectors for every audio, and I concatenate these vectors from several audio files to have more data. And then we compute the cost, which is cosine similarity. And then we apply this function, which actually computes the transformation matrix. How does this metric look like? It looks as follows. It says how much of goods we should uh, take from one source, from another source. Let me draw this illustration. Uh, so if we have, oh no, it's here. So if we have this transportation problem, the transport plan, this pi, the function which is joint distribution, will look, in this case, it will be 3 by 4 matrix. What's that? Um, oh, really? Let me use this. It will be um, 3 by 4 matrix. And it will contain some weights, some numbers. So, for example, it will have weight W, oh, I don't know, W11, W21, W31. And it means that we should, let's say we have, I don't know, X1 units here, X2 units here, of some goods, X3 units on the third manufacturer. So it means that the demand of the first um, store, for example, we will satisfy with W1. It's just the coefficient, the fraction of the goods from the first manufacturer plus W21 times X2. So this fraction from the second manufacturer. And so we will have like these lines from this, and from that one. Plus W31 times X3. So this matrix will contain this, what is called transportation plan. And it will be 3 by 4 in this case. In our case with audio, we have, so let me erase this. So yeah, it sounds like probability spaces, multi-dimensional distribution. It sounds complicated. In discrete cases, just some matrix. Um, of course, in continuous case, it's continuous distribution. But that's why this problem students solve in class, and more general transfer problem they never heard about. uh, okay. So in our case of audio, we have um, for example, audio um, of one speaker and audio of the another speaker for for example, target and a source. And we transformed this into vectors, vector embeddings with our WAF-LM model, WAF-LM, WAF-LM. So let's say we have several hundreds of embeddings for source and several hundreds of embeddings for the target speaker. So optimal transport plan, this algorithm is called Sinkhorn by the name of one person who proved the convergence of this algorithm. This algorithm actually was known several years before, but he proved the convergence. We'll build a matrix of this shape times this shape. And after we have this matrix, we can represent, let's call this, for example, vector x1, well, or y1, y2, and so on. And this vector is x1, x2, and so on. So we can represent the first, not represent, but match the first vector with a linear combination of the vectors from the target. So it's kind of how much of vector x1 we should use, how much of vector x2 we should use, how much of vector x3 we should transport, in this case, use to match vector y1. So times x1 plus so what was that like? I think it was w21 x2 and so on. So we represent the first vector as a linear combination of the vectors from our target speaker. Then we will replace the second vector with linear combination, but with different weights from our target speaker. So we will replace these embeddings with new embeddings obtained by this transport plan. And let's listen for the result. So this is our source, the recording of a woman.
And that if she noticed anything odd or out of place, she would never rest until she had ferreted out the whys and wherefores thereof.
And this is the reconstruction when we mapped these embeddings into embeddings of the other person.
And that if she noticed anything odd or out of place, she would never rest until she had ferreted out the whys and wherefores thereof.
And this is the entire code for this project. So, um, as I said, I believe the optimal transport will become as popular as a diffusion model. And if we have time, I will explain actually their connection, because one now let's talk about neural optimal transport. So it works fine, but the problem is that if you want to apply this in online setup, like you pronounce something and you want that this model converts immediately your voice to the target speaker, you can't use this discrete optimal transport, because discrete optimal transport just creates this matrix of this optimal transport plan. for given vector, for given data. So if you want to convert a new sentence, you will need to evaluate this transport matrix again. We know neural networks. Why don't we learn a neural network that actually maps embeddings of one distribution to embeddings of another distribution? And and this is called neural optimal transport. Let's talk about neural optimal transport. Oh, we almost don't have time. Okay, let me open the notebook. So for neural optimal transport, you can play with it. They have the code in under seminars, strong optimal transport. Just explain what's the difference between strong and weak optimal transport. So if you apply the conditional probability rule, then the joint distribution can be represented as conditional times the marginal. And in this case, this conditional distribution will represent not just one point, but a distribution for one x point, you will have actually distribution. And this setup is called weak optimal transport. So in this case, from one point, you can generate multiple data. If you use the standard even neural optimal transport, you will be able to generate just one image or audio. So in this paper, a neural optimal transport, they generated, for example, one domain was bags, another domain was shoes. And so X and Y domains, and neural network learned this transformation that transformed bags into shoes, or another example, real faces and avatars. Males to females. So um, um, this is example of the weak optimal transport when we can generate several images from one. So, for example, Z stands for the Gaussian noise with different magnitude, different variance, and you can see that when the variance increases, we have less similar images. So this is another example, landscape to the cathedrals. So for small noise, uh, you can see it here. For example, this um, what's called this clouds, I think. So for small noise, you can see that clouds were preserved. For larger noise, there are no clouds. So for smaller noise, it preserves more details. But let's talk about let's look at the example. Where is it? So in this notebook, they apply optimal transport on just Gaussian distribution and on MNIST data set. They also have notebook for weak optimal transport. So let's okay, and this is the most complicated part. So we started from this cost function. Uh, there's this theorem. It's actually prepared us with derivations, but well, we don't have time. The theorem, which is called um, oh, it doesn't matter. I wrote it somewhere. So the optimal transport, Kantarovich actually received the Nobel Prize for this problem. And the main like impact was that he introduced so-called dual formulation of this problem. You remember when we talked about support vector machine, we also used dual formulation, and so in the transport problem, he introduced dual formulation instead of looking for the transport map. We can introduce two functions. If you think about intuition, the intuition of this function is as follows. Instead of transporting these goods by yourself, you can hire a contractor, and contractor will first purchase these products, and then it will actually transport to you these products. And these are two functions. One is the cost of the purchase, another is the cost of the then transporting these goods. So it's called dual formulation. And yeah, we don't have time to talk like about in details of this, but it's the main idea that we can reformulate this problem as the game problem, like guns, when we minimize and maximize our loss function with respect to functions. And in the difference with guns is that they requires that these functions satisfy Lipschitz condition. In this case, these functions can be arbitrary, and we will just use two neural networks for these functions. And of course, these integrals we will replace by Monte Carlo estimation. We will just sample some images and calculate the cost of images. And let's look at the examples. So actually they provide also derivations, some derivations here, but I didn't understand those derivations, so that's why I wrote my own. But there is a book, I also posted a link on the book, which is called Computational Optimal Transports, where you can read all the details actually. So let's try to run this notebook. So first they create a simple data set. I hope it will work. I just want to show how fast it works, but now it's just so they created two data sets, Gaussian and a mixture of Gaussians. And then they define cost function as the just square distance, L2 Euclidean distance. And then you remember we should define just two functions, and they define two neural networks. The input shape is 2, output shape is 2. And for F, the output shape is 1, because it's kind of discriminator if we think about GANs. T is generator, it will transform our images F. And we initialize this to optimizers, one each for, and here is the entire algorithm. So we generate a bunch of images from one set and another set, and we approximate the integrals. There are three terms, but the first term doesn't depend on f, so that's why here we have two terms. And here one of the terms didn't depend on t, so also here we have two terms. And use the Monte Carlo estimation. And like, and perform one step for neural network F and several steps for neural network T. In Gaussian's contrary, we perform one step for generate and multiple steps for generate. So these are the differences between. There are similarities and differences between with GANs. And finally, this is the training. And this is how we start from Gaussian distribution. And then these lines, they show the path. Actually, yeah, it's still around. They show path how these points were moved to the target distribution. So this is the target distribution. This is the intermediate result of our neural network. You can see that this T transform plane is learning, and our original points are mapped into the target distribution. And there is another example. I won't run this on MNIST dataset and USPS dataset. They both have images, but the style is different. So now, because these are images, they used convolutional neural network. And the first line is MNIST, the second line is transformed, the last line is the second data set. And you can see the transformed images, they look like images in the target data set. Okay, I think we should stop here for today. And yeah, I hope you learned something new, one new model. Okay.